Hello everyone, this is Professor DiPolo welcoming you back to Psych 265 Fully Online. And in today's lesson, we're going to be talking about two group experimental design. So when we have to decide what kind of study we're going to run, there's multiple decisions to be made. I talked previously about correlational design and the limitations with correlational design, in that you cannot draw cause and effect conclusions from a correlational design. In this chapter, we're going to be talking about one way to draw a cause and effect conclusion, and that is with a simple experiment. And the simplest experiment is with two groups. The other benefit of doing an experimental design, besides drawing cause and effect conclusions, is that you control for the extraneous variables, or the variables that you're not controlling for that can influence the results of your study. So that's very important. And you establish something called temporal precedence. So you establish what comes first and what leads to what comes after. So that's the cause and effect part. So with the two-group design, you have covariation. Changes in one variable are associated with changes in another variable. So you're manipulating something. One group gets the treatment, the other group gets the control, and then you decide, is the difference between treatment and control, does that reflect on whatever the dependent variable you're measuring? So you're looking at, is the change in the treatment group, treatment versus control, associated with covariation in the dependent variable, so whatever the target variable you're interested in studying. And temporal precedence is cause and effect. So if I manipulate my independent variable at time 1, that's going to lead to a change in the dependent variable at a later time, at time 2. So you definitely have time 1 leads to time 2. For example, in my meditation studies I've been running at BMCC, I assigned people to either get meditation or they got a control group, which is stress management, basic stress management. And I initiated that over a period of 8 weeks. And then 8 weeks later, I measured their levels of anxiety and depression and somatization. So what I was manipulating at the beginning, which is whether they got the meditation or they got the stress management, which I'm calling the control condition, that the difference between those two groups led to a difference in the dependent variable, which was anxiety, depression, and somatization, which is physical symptoms. And the change in the group between meditation and stress management affected something at a later time, which was their levels of depression, anxiety, and somatization. So there was a temporal precedence there. The change at time 1 led to a difference at time 2 in the dependent variable. And you want to rule out extraneous variables. In experimental design, we'll always rule out extraneous variables if you use random assignment to the conditions or to the groups. In a correlational design, you just look to see if 2 or more variables are associated. But that doesn't mean anything, because you can't say that one variable leads to a change in another variable, because with a correlational design, you're not controlling anything. You're just looking at, do 2 or more variables go together? When you do an experimental design and you use random assignment to conditions, you are eliminating everything except for what you are manipulating, which is the independent variable. Any other variable that could influence your outcome measure, your dependent variable, is called an extraneous variable. And those are all controlled for once you use random assignment. For example, in my study, I was looking at meditation versus stress management in terms of depression. That's one of my dependent variables, was depression. And the reason why there's no confounding or extraneous variables there is I randomly assigned people to either get to get meditation or to get the control group, which was a basic course of stress management. Now, if I didn't use random assignment and I didn't run an experiment and I ran a correlation, yes, I would see that there's a correlation between the amount of time people meditate and their levels of stress, their depression, anxiety, right? You would expect that if they meditate more, they're going to have less stress, anxiety, depression. But you cannot conclude based on a correlation that I'm causing this. So meditation does not cause you right, under a correlational design to have lower levels of stress. It's just associated with. The only way I can rule out any other variables that can influence that, which could be, there's numerous variables other than meditation, which can lead to depression, right? Social isolation, loneliness, uh, income, socioeconomic status. I mean, these are all factors that can influence depression, stress, etc. But if I'm running an experiment, I'm controlling for all those factors by using random assignment, randomly assigning people to groups, to either the treatment group, the meditation group, or to the control group, which is the stress management group. So if I'm using random assignment and I'm running an experiment, all those other miscellaneous factors that could influence depression and stress, they're irrelevant because they kind of balance out. So all the participants in the two groups are balanced with regard to everything except for what I am manipulating directly, the independent variable, which in this case would be meditation versus stress management. And by ruling out and controlling these extraneous or confounding variables, my experiment has something called high internal validity. And this is the degree to which we are confident in drawing cause and effect relationships. Any experiment that uses random assignment will have high internal validity. That means I'm confident saying it's cause and effect. Any correlational study will have low internal validity because you cannot draw cause and effect from a correlation. So I need to manipulate the independent variable, and basically started talking about this already. I have to decide what kind of experiment do I want to run. Do I want to run an experiment in the lab where I have a lot of control over the variables that I'm manipulating, the independent variable? Or do I want to run the experiment in the real world? Right. And if I run the experiment in the real world, in the situation in which this behavior generally occurs, then the experiment has high mundane realism. Mundane realism is you've done the research that will apply directly to everyday life. And the best way to get mundane realism is run the study in real life. The problem with that is if you run the study in real life, you're losing control because real life is not a laboratory. Like anything can happen. The unexpected events can happen while you're trying to run your study if you're doing it in real time, in the environment, right? In a day-to-day life situation. If you're running it in the lab, you have complete control over what you're doing. You shut the door, no one comes in, no one bothers. There's no other confounding or extraneous variable that can screw things up. But if you're doing it in real life, there's tons of things that can screw things up, right? For example, let's say you're doing an experiment in real life and then there's a natural disaster. Well, that's not anticipated, right? And that's going to screw up the results of your study. Or you do the experiment in real life and then all of a sudden a group of people come out of nowhere and interfere with the behavior of the person that you're observing. Well, that wasn't planned. That wouldn't happen in a lab, but that happens in real life. So, there is a benefit of trying to make your study as realistic as possible, but that comes with a cost. The cost is control. You're going to have extraneous or confounding variables if you run your study in the real world setting. You're not going to have that if you run your study in the lab. But then again, if you run your study in the lab, then people will say, well, it works in the lab. Does it work in the real world? It's similar to like when you run a study on animals. This drug works well in animals. This vaccine works well in animals. So therefore, will it work in humans? Maybe, maybe not. It works in the lab with animals, but the lab in animals is not real life. So there's trade-off whether you want to do things in the lab. I suggest doing things in the lab first. Establish that something works in the lab before you try to take it out of the lab. That's probably the best solution for, generalizing your results to real world situations. Now in the basic experiment, we call this the two-group design or the simple experiment. You have two groups, usually an experimental or treatment group, and then your control group. We generally expect that the treatment group should do better in some way than the control group. That's the goal. That's what we always want. We do not want the control group generally to do better than the treatment. That would mean our experiment is kind of, we were lost. Our hypothesis was not correct. The experimental group is the group that gets the treatment. So in my study, it's the group that got the meditation because I wanted to see if meditation reduces anxiety, stress, somatization, etc. So the experimental group is the group that got the meditation. The control group is the group that did it. So I gave them stress management as a control just because I wanted to compare meditation to stress management, right? I want to say that meditation is superior to stress management techniques, things you learn in like a stress management class with regard to treating anxiety, depression, somatization. And that's what I did show in my studies. The meditation is superior. Now, your control group could be anything you want to compare it to. It could be one group gets meditation and the control group gets nothing, right? Or the control group listens to some relaxing music, or the control group, is told that the study is delayed and they have to wait to participate. They basically get nothing for that whole period. Uh, it's up to you to decide what your control group is going to be. But generally, I like a control group that is a little bit more than the people do nothing or do something completely unrelated. I want the control group to be somewhat related, and I want to show that my treatment is better than that control group. But that's really up to the researcher to decide what kind of control group. Do you want a control group as a comparison? Like I have stress management as a comparison to my meditation group? Or do you want your control group to be basically nothing? Send them home and have them go to sleep for 2 hours and the other group meditates for 2 hours. So that's really, a matter of preference, but you're always comparing your experimental group to your control group, and you want your experimental group to be superior to the control group. And experimental control is basically what I was talking about with regards to random assignment. So when you randomly assign participants to conditions, you keep both groups the same with regard to any kind of variable except for the variable you're manipulating, right? In my experiment, my independent variable was meditation. And the way I kept the groups equal is I randomly assigned people to either get meditation or they got the control group, which was stress management. Okay. Both groups were relatively equal on any other variable except for meditation. One group got meditation, the other group did not. But they were balanced out with regard to gender, with regard to age, with regard to socioeconomic status, with regard to level of stress in their life, etc. And the reason why they were balanced out, they were kept equal, is because I used random assignment. And if you use random assignment, which means you flip a coin, you go to this group, you're in the treatment group, you're in the control group, right? Just keep flipping a coin and then balance out the groups that way. If I do that, then those groups are relatively equal with regard to everything except for the variable being manipulated, which is the independent variable. And that's what you want. That's the purpose of having an experimental control group. Now, after I have my control group and my treatment group, I need to have my dependent variable measured. So I need to come up with an operational definition or a way to measure the target variable or the dependent variable. In my experiment, I had multiple dependent variables, but one of them was depression. So I needed a way to measure depression. Now, I prefer to do surveys. And you probably have learned this throughout the course is, I am not a big fan of interviewing. I mean, I've done it before, but I don't consider myself a really good interviewer. And I just like surveys because they're not perfect, but you gather a lot of data and it's a lot easier to run. It's a lot less money. But you could do interviews if you train people to do interviews. It's a lot more work, and then you have to code the interviews into some kind of quantitative dimension usually. But this is self-report data, whether it's interviews or surveys, the participants basically answer how they want to answer. And if I'm asking about depression, I give them a survey, are they going to be 100% honest with me all the time? And the answer is probably not. But are they going to be honest if you do an interview? Probably not either. right? So there are pitfalls with any kind of self-report measure, whether you use surveys or interviews. There's always, there's pitfalls, but there's still a good measure. For the most part, people answer surveys or scales of depression pretty honestly. Maybe not entirely honestly, but pretty honestly. So you're getting some good data. It's not 100% good data, but it's pretty good data. I've also used behavioral measures. So these are measures that could be reaction time on a computer task. You give them the duration of a response, where you time the response that you're looking at. You can do physiological measures. I've done EEG based measures. I've done in the past fMRI based measures. So these are, I think, better measures than just self-report. I mean, self-report's helpful, but having a behavioral measure to go along with self-report kind of, allows you to feel more confident in the data that you have. It's expensive. MRI is crazy expensive. Like we don't, with all of CUNY has no MRI machines. So even if you wanted to do an MRI within the CUNY system, no one has it. I did my MRI research at Rutgers, and Rutgers has uh, one of the strongest MRI, best MRIs in the country. They just bought it recently. That's a 4 Tesla magnet. It's really precise. And it's extremely expensive, and they used to share it with the UMDMJ Medical School. So the machine really belonged to the medical school, but they would let us use it at night. And we had to pay for it, obviously. It was $500 an hour to use the machine, just to use it. And it's quite expensive research, but it's interesting research. And I think it complements the self-report measures pretty well. So if you can use both, if you can afford both, whether it's EEG, which is looking at brain waves, and I'm looking at that now at BMCC. I'm using a portable EEG device that has like 4 channels, and I'm looking at responses. Well, was looking at responses until recently, and so I'm using that right now. I've done MRI in the past. GSR is galvanic skin response, so it's the electrical activity of your skin, and when you're stressed, you tend to have higher levels of GSR. So these are very interesting measures. So now that we know what we're doing with regard to how to measure the dependent variable, we're going to then formulate our hypotheses. Our experimental hypothesis is kind of what we want to happen. This is our goal of the research. So it's a clear and specific prediction of how the independent variable will influence the dependent variable, and is generally what you believe is going to happen. That's your experimental hypothesis. So in my experiment on meditation, my experimental hypothesis is that meditation will be superior to stress management, my control group, with regard to levels of depression, somatization, and anxiety. And that's kind of what I found for the most part. So the experimental hypothesis is what you want to happen. It's your prediction of what you expect to happen. It's what you want to happen. It could be either directional. Directional means that you're specifying a direction of the effect. So in my research, I specified the direction. So I said that meditation will lower levels of stress, anxiety, and depression. So that word lower means it's a directional hypothesis because I'm indicating the direction of the anticipated effect, that there's going to be a decrease. If you expect an increase, that would also be directional. Non-directional means that you're not specifying a direction of the effect. So you're just saying, instead of saying increase or decrease, you're saying a change is going to happen. So in this example, daily walking will lead to a change in levels of depression. That is a non-directional hypothesis because you don't know if it's going to increase depression or decrease depression. You're just saying a change. And so a non-directional hypothesis is useful when you're not 100% certain what's going to happen, right? So you have an idea that what you're doing is going to work in some way, but you're not 100% certain of how it's going to work. So then use a non-directional hypothesis to be on the safe side. And when you publish things, publishers expect you to be using a non-directional hypothesis. And the reason being is that it's harder to find the effect that you want if you're using a non-directional hypothesis. It's much easier to find the effect that you want by using a directional hypothesis. The problem with using a directional hypothesis is sometimes we have an idea of what's happening, and then the result ends up being the opposite of what we originally thought. And if you're using a directional hypothesis and your results end up being the opposite of what you thought, you're never going to reject you're not going to be able to claim anything. You're not going to be able to reject technically the null hypothesis. So directional is a useful hypothesis, but when it comes to publishing research, most publishers, most journals would expect you to statistically test using a non-directional hypothesis. So you set your hypothesis, you have your experimental design set up, now you need participants. And the main sort of choice here is between random sampling versus convenience sampling. In psychology, it's much easier to use a convenience sample. Convenience sample means you ask people, do you want to be in my study? Are you available? And if they say yes, great, you're in my study. Are you available? Great, you're in my study. And you just go wherever you want. I can stand in front of the school cafeteria and ask people, do you want to be in my study? That would be a convenience sample. The problem with a convenience sample is, although it's easy to get, it may not be representative of the population in which you're trying to draw conclusions about. So if I'm looking at BMCC students, the population of BMCC students, there's 20-something thousand students. If I just go to the cafeteria on a Wednesday afternoon and just take 50 people in the cafeteria at 2 p.m., the students I took in my sample that were in the cafeteria at 2 p.m. on a Wednesday may not be representative of the entire population. Maybe these are students that take like morning and afternoon classes, and those students are different than the students that take night and weekend classes. Maybe those students that eat at the cafeteria are somehow different than students that bring their own lunch, right? I don't know. Or students that go outside and eat somewhere else. Possibly, right? I mean, you're just grabbing whoever's available. Random sampling doesn't have that problem because with random sampling, every member of the population has an equal chance of being in the sample. So if I took a random sample of BMCC students, I would take some of the students would be on the weekend. Some of the students would be taking night classes. Some of the students would be taking day classes, right? I mean, if I took a truly random sample, every student at BMCC, which is every member of the population, would have an equal chance of being in my sample. And that would be a better sample because I'd be more confident if I used that sample and I found something to work. Because then I could say these students are really representative of BMCC because some of them are evening students, some of them are older students, some of them are younger students, as opposed to a convenience sample where I'm just taking who's available. So that simple random sample is a better sample overall, and it allows me to draw stronger conclusions about the population. The problem is that it takes so much time to do a random sample, and it's very difficult. I mean, I would have to schedule myself all hours of the day and night and on the weekends. So that means if I need to take someone that comes in Saturday night at 10 p.m. for a class, I'd have to be on campus Saturday night at 10 p.m. And then the next person might be Sunday morning at 7 a.m. So then I'm back on campus Sunday morning at 7 a.m. And you can see how that would be a real trial to like be moving around scheduling things like this. It would be very difficult. And so as a result, it's a little too difficult to expect people to take random samples in their experiments. So we mostly go with convenience samples. And then the goal with convenience sample is you must replicate. So if you get a result in your study with a convenience sample, you need to replicate, which means run the study again with different people and hopefully get the same result. So replication, which is repeating the study with different individuals, is more important with a convenience sample than a random sample. The problem is that a random sample is just not realistic for most researchers. I mean, it's possible. It's possible to do a random sample, it's just not realistic for most people to do. So now we have to put people into groups. So if I have a two-group study, I need to assign people to one of those two groups. And it's very important that those participants are individual. That means they don't talk to other participants. They don't act collectively in any way. We want to make sure each participant is kind of on their own to react to the study. We want to separate participants. You don't want your participants talking to each other about the study before they take the study. Or you don't want a participant that already took the study to then talk to a future participant about the study, because that's going to contaminate and bias your results. So you want to keep these participants kind of isolated, not together. Then you want to use random assignment. So each participant should be randomly assigned to, in this case, our two groups. So in my study on meditation, they were randomly assigned to either get meditation or to get my stress management control group. And each participant should have an equal chance of being in either the treatment group or the control group. That's random assignment. That is vital. Without random assignment, you do not have an experiment. You have a correlation, because then we don't know if confounds or extraneous variables are influencing the results. With random assignment, there are no extraneous or confounding variables, which are the alternative explanations. They go away. They're balanced out. So random assignment allows you to draw cause and effect conclusions in your experiment. That's why it's vital. It's probably the most important thing that when you design your study is that you use random assignment. However, sometimes we don't have what is called independent groups. So sometimes we can't just randomly assign each person to one group. In some experiments, we have what is called repeated measures or correlated groups design. In those repeated measures or correlated groups design, we have the same individual or we have pairs of very similar individuals that participate in more than one condition. So for example, if you wanted to look at twins, and you wanted to count the twins as like basically the same person because genetically they're 100% the same if they're monozygotic twins, right? We can put them in an experiment, we can give them different conditions, and we would statistically treat them as if they were the same person because they're very highly correlated. They're identical twins. I mean, there's not two people in the world that are more highly correlated than identical twins. Even if you look at identical twins reared apart, they show very similar characteristics and behaviors and preferences. So if I wanted to take twins, monozygotic or identical twins, and then assign them to, one twin goes to the treatment group and the other twin goes to the control group, statistically, I could almost treat them like one person gets both the treatment group and the control group. The independent variable, both levels of the independent variable, right? So statistically, I treat them almost as if they're the same person. And this is known as a matched pairs design. So I take two people that are highly correlated, like twins, and then I randomly assign each person to either the experimental or the treatment condition or to the control condition. And I treat them as if they were one person because they are highly correlated, right? They're very similar. So statistically, I treat them as if they're one person. And this is known as a repeated measure design. So I treat them as if they got the control, and then I treat them as if the same person got the experimental group. And why would you do this statistically? Well, statistically, it's easier to support your hypothesis if you run a design called repeated measures, which means you have the same person getting both the treatment and the control condition at different times. rather than an independent groups design where I randomly assign people to either get the treatment or the control. So statistically, this is a better design. And you could use it as matched pairs, or you could have the same exact individual get the treatment in the control group. The problem with having one individual get both the treatment and the control group is that that individual can be influenced. So let's say the individual got meditation first, and then I measured their level of depression. And then 2 weeks later, I gave them stress management, and I measured their level of depression. That same person could be contaminated because the effect of meditation may last longer and interfere with the same person getting the stress management condition, right? So even if I spread it out by like a month or 2 months, the effect of getting meditation first still might interfere with giving them the stress management training afterwards. So the design that I ran is not conducive to using this repeated measures. However, if I had identical twins and I gave one of the pairs of twins the meditation and I gave the other twin the control, the stress management, that's okay because they're two different people. So genetically, they're 100% equal, and they're very, very highly correlated, right, in terms of their behavior and their dispositions and their preferences. But they're not getting two treatments. They're only getting one. Versus if I have the same person take the meditation and then wait a month and then take the stress management, and there could be contamination there. So that would be one reason why, if I wanted to run this study as repeated measures, I could use what's called the match pairs design. Now we have to develop a protocol. This is a step-for-step plan for what participants will do throughout the experiment. You want to keep these steps identical for all participants so you don't have any confound that influences the dependent variable. As I mentioned before, experimental realism, well, I talked about mundane realism, but experimental realism is basically the degree to which the participant is able to be manipulated in the lab. So it's the degree to which the manipulation works in the lab. It has nothing to do with real life. That's mundane realism. Experimental realism is the impact of the independent variable in the lab studied. So that's important. If you're doing it in the lab, you want to make sure that whatever independent variable you're manipulating has a big effect. And to sort of boost the experimental realism, a lot of times you have to hire confederates. These are helpers or accomplices of the experimenter. And if you remember the famous Milgram study, the obedience study with the electrical shocks, the confederate in the study pretended like he was getting zapped and that he had a heart condition. And the reason he did that was to really make the participant believe that they were really hurting him, that they could kill him. That was to make the experiment more real. That was increasing experimental realism. So the confederate was like screaming and he was saying, my heart, you're hurting me. You're hurting me. I have a heart condition. Please stop. That was all an acting job. That guy was a confederate. He was working for the experimenter, and he was acting like this to make sure the participant felt stressed and felt like, I could really hurt this person. Should I really continue? And it made the impact of the obedience a much more, poignant, much more real. Because, I could really hurt this person if I continue, but the experimenter's telling me I must continue. And so what do I do? And unfortunately, what they did was listen to the experimenter. Despite the guy crying, they thought he was a real person. That he had a real heart condition. And that was important to make the experiment stand out and to make it feel more real. That was increasing experimental realism. A researcher also wants to keep notes during the study to learn, does the participant really believe that the experiment is working? Is it real? Is the participant suspicious? Because if your participant is suspicious of something you're doing, you're not going to get a true response, and you're going to probably have to eliminate that person's data. So in the Milgram study, if anybody realized that this whole thing was a scam, that this person was faking it, and this person was an actor, and he didn't have a heart condition, if they realized that, that person would be eliminated from the data collection because that person does not believe in the experiment. It's a biased result. So you have to eliminate that participant that really doesn't buy into the whole story of what's happening. And researcher notes will help you with that. Determine who's believing in it and who's suspicious. You would also want to do a manipulation check, which is a measure that other than the dependent variable, right? So it's something else that changes other than the dependent variable in a study. For example, in the Milgram study, which is about obedience, so they're really interested in looking at obedience, but they could ask the participant about memory. Do you feel that the shocks are motivating you to remember the information better? That would be a manipulation check. That you would ask a question to see if the actual independent variable is having an influence. So it's something other than the dependent variable that you can check each participant for to make sure that the independent variable is being effectively manipulated. So in my study, I was looking at meditation and its effect on stress and anxiety and depression. And so what I could simply do is after they got their meditation session, I could ask them, do you feel any different after you had the meditation? And if the participant says, yeah, I feel more relaxed, or I feel lighter, then that would indicate that the meditation is working. That's a manipulation check. So that's not my dependent variable. My dependent variable is anxiety and depression. But if I just ask them, how do they feel? And they say, I feel lighter, I feel calmer, that would give me evidence that whatever I'm doing is working, that the meditation is actually having an effect. And so some researchers like to use this to make sure that their manipulation is working. Other researchers are afraid to use this because they think that if they ask a question that's related somewhat to the dependent variable, that they may get some sort of distorted answer. So if they ask a question about, relaxation, that's going to influence what they report in terms of their anxiety levels, because that tips them off to like what the experiment's about. So I don't know how I feel about manipulation checks. I generally don't do them, but many researchers do, just to make sure that what I would suggest instead of doing manipulation check is you run a pilot study. So you run a trial study and you see what happens. And I think that's a better way to know that what you're doing is working than asking a related but not the same question, something related to the dependent variable but not something different, to see if there's actually a difference. I don't know how I feel about it. I don't really use it in my research very often. I'd rather run a pilot study. Now we ran our study, we checked our manipulation if you wanted to do that, and we're ready to analyze the data. For two groups, we're going to use a t-test for independent means, which is also known as a between groups t-test. For those that haven't taken my stats class, for those that have taken my stats class, you already know all this, right? And we compare the means of the two groups. So we compare the mean of the treatment group with the mean of the control group. And we want to determine, is the difference due to chance, or is the difference due to the effect of the independent variable? So running that t-test, we run it on a computer, it spits out information, and it tells us, is the difference real, or is it due to chance? We don't want it to be due to chance. We want the difference to be real, because that means that the independent variable is having an effect on the dependent variable. If it's due to chance, that just means that by luck, there's a difference, and it's not really meaningful in any way. We could also look at effect size. So what is the true magnitude of the independent variable? Does it have a big effect, a small effect, etc.? Medium effect, that's effect size. Statistical measure of the magnitude of the difference between groups. We want to compare this test to our null hypothesis. So remember I talked about experimental hypothesis, and this is kind of what you want to show. This is what you believe in. The null hypothesis is the opposite of the experimental hypothesis. The null hypothesis always says there's no difference. So there's no difference between groups, or there's no effect of the independent variable. We want to always reject the null hypothesis. Always. Because if we reject the null hypothesis, we can then support the experimental hypothesis or the treatment hypothesis and say that our independent variable works, or there's a difference between these two groups, the treatment group and the control group. So we always want to reject the null hypothesis under every circumstance. Here's what it looks like when you write it out in a journal. T is the name of the test. In parentheses, you have something called the degrees of freedom, which in this case is the number of subjects minus 2. And there's various formulas for the degrees of freedom, and that's more of a statistical item that I'm not going to really harp on in this class. But if you take stats, you're going to have to learn about degrees of freedom eventually. You have the t-score, so this is basically whatever the output is, whether you're using a computer or doing it by hand. And then you have your p-value, which is our significance level. And we want that p-value to be less than 0.05, which means there's less than a 5% chance that the results you got are due to luck. So we want it less than 0.05 because that means there's less than a 5% chance that the difference between the treatment group and the control group is due to just luck. You lucked into a result. And if you didn't luck into the result, then the result is real. So the magic number here is 0.05. Anything less than 0.05, and you support your hypothesis, the experimental hypothesis. Anything greater than 0.05, you fail to reject the null hypothesis, and you're not happy because you didn't show anything that you wanted to show. You showed that your idea is inconclusive at best. So that's the p-value, and the magic number there is 0.05. And then you have D, which is effect size. It's something called Cohen's D. And this just shows you how strong the independent variable is. Is it a very small effect, or is it a medium effect or a large effect? The larger this D value is, the stronger the impact of the independent variable. So of the treatment group, the more effective the treatment group, the larger the D value. And this is more statistical, but I'm just going through the sort of write-up. And then you can make a bar graph. So here's a bar graph showing two groups. One bar will be the treatment group, the other bar will be the control group, and then you could look for differences. And you could actually put error bars on top to actually make this more clearer. In this graph, it looks like high restriction leads to a greater quiz score than low restriction, whatever that means. I can't really tell what that means without any sort of background. But this is what you would plot. You would always plot a bar graph if you're looking at a two-group independent groups design. This is the kind of graphical measure you would show. And many people do all kinds of crazy things with bar graphs to kind of exaggerate them. You want to do an honest bar graph, and this example is an honest bar graph. As you see that it starts at 0 and it goes to 100. This is the way you would want to draw the bar graph. I've seen people do really screwy things. So you see like the difference is very small here between these two bars. I've seen people start the bar at 60% and end it at 80% and then blow this up. So like kind of elongate it, put 60% at the bottom where 0% is here, and put 80% at the top where 100% is, and kind of stretch it out to make it look like it's a bigger difference by stretching the scale of the y-axis. I've seen people do this a lot. Don't do this. This is just really petty and silliness, and people trying to mislead and show that their research is better than it ended up being, right? If you have a good difference, then your idea was good. If you have very little difference, then your idea maybe not so good, and just accept it and move on. In this case, there's not much of a difference. I'm not too blown away. In my studies that I ran, there is a big difference. With a small number of subjects even, I get big differences. So there's a very powerful effect. It really depends on your research. If you have a very small effect, it's probably not worth publishing. Even if it is significant, even if you had thousands of people in your study, if it's a very small difference, really, what does that mean? What does that tell the audience? Not much. It tells the audience that you had a big sample and you were able to reject the null hypothesis because you had a big sample. It doesn't show that this is a really powerful effect, because in this graph, there's not really much of a powerful effect here. It's a very small effect. So just a review of the different concepts. The independent variable is what you're manipulating. In this case, we have two groups. In my study, meditation was one level of the independent variable, and the control group was the other level, the stress management group. So my study had one independent variable and two levels, meditation and stress management. So levels is the number of groups. In a two-group design, you're always going to have two levels. If you have more than two levels, then you're not doing t-test, you're going to be doing what's called a NOVA. Experimental group, that level gets the treatment. The control group, the second level, does not get the treatment. And the dependent variable is what you're measuring. And the operational definition is how you're measuring it. So what are you doing to measure the dependent variable? What steps are you using? That's your operational definition. That could differ depending on the researcher. Different people have different operational definitions of variables. The manipulation check, I said before, it's a variable other than the dependent variable that you can check to see if there's a difference. It should be related to the dependent variable, but it should not be the same thing. And as I said before, I'm not a huge fan of this. I'd rather just run the pilot study first to make sure the manipulation works, and then run the full study. I think that's better because you also realize other problems when you run the pilot study. You run that pilot study on maybe 20 people, 10 or 20 people, and there's a lot of problems with your study. And then you can go back and fix them before you run your study on 100 to 200 people. So I like the idea of a pilot study better than the manipulation check. Some researchers use this. I personally don't. But I would say some people do. A minority of people do. But people do. And obviously the control group is necessary because you want to see if your treatment group is there a difference? Is there a statistical difference between your treatment group and your control group? You need a control group because otherwise your treatment group has nothing to compare it to. So a good example of this is if you're testing a drug. You're always running a drug against a placebo, which is a sugar pill. The drug has to be better than the placebo. If the drug is not better than the placebo, then the drug can't be approved. And the reason is there's a placebo effect, right? So people thinking they get the drug, but they get the placebo, just thinking you're going to get better helps you get better. And that's the placebo effect. The real drug has to be better than that. Otherwise, how can you charge people all kinds of money for it when it's not better than a sugar pill? So this comparison group is always important. So you should always have a control group in every experiment you do. That control group could be something similar, like I ran with the meditation study. I had stress management as a control group, a comparison group. Or your control group could be completely different, right? You could just have people, sit in front of the computer and, sing songs or listen to music. That could be the control group, but I could compare that to meditation. It's really up to the experimenter what the control group or comparison group is. But you have to have a control group. You have to have some means of comparison. That's not optional. And just a review of experimental versus mundane. Experimental is sort of the degree to which the participants believe that the study is working. And the Milgram study is a good example of that. They actually believed that this person was actually getting the shocks and they were actually hurting them. So they strongly believed in the study, right? What was being manipulated there. And so that study, the Milgram study, had very high experimental realism. Mundane realism is how can you generalize the results in the lab to the real world? Can you do the study that parallels real world situations? And that's important. I mean, you want to do things in the lab first. So my suggestion is make sure the manipulation works in the lab before you start trying to take it out of the lab to increase your mundane realism. And so that's about it for this week's experimental class in research methods. Hope you enjoyed this. I'm available through email and Zoom or whatever, office hours, etc. So if you have a question, feel free to reach out to me, and I'll see you next time.